All right, this is the bouncing spring problem, and we're given some information about the motion of a spring. We are told we can assume it's sinusoidal, so that means that we can use a sine or a cosine wave to model its behavior. And then we're given a couple of key points. We know that when our stopwatch reads 0.3 seconds, the weight is at its highest point of 60 centimeters, and that it hits its low point of 40 centimeters at t equals 1.8. So I'm just going to sketch that really quick to give me a visual. I think that's really helpful. So we have a minimum of 40 and a maximum of 60. And we hit the first one. Okay, so 0.3 is a maximum. And then if we just continue that scale, 6, 9, 1.2, 1.5, 1.8 will be a minimum. Okay, so that's really only half a period, max to min. So I don't know if I left myself exactly enough room, but what was that? That was 1.5 seconds. So after another 1.5 seconds, we'll have to scrunch a little. We should be back up to a maximum. 1.8 plus 1.5 is 3.3. So if we need it, that's a 3.360. So there's a full period of my function. Notice that what we just did there was calculate that the period is 3 seconds. So we've got that, and if the period is 3 seconds, then our b value has to equal 2 pi divided by 3. So I'm getting part of my function already. I also can tell that the total height of my sine wave is from 40 to 60, which is a total of 20 units. What are my centimeters? 20 centimeters, which means that exactly in the middle of that at 50 is my equilibrium, and half of that, 10 centimeters, is my amplitude. I go up and down 10 centimeters from equilibrium. So I'm getting a pretty good start. I'm going to put a 10 out in front of my trig function. I haven't decided if I want a sine or a cosine yet, so I'm just going to save that for a second. My b is 2 pi over 3. Then we'll leave this so that we can put a shift in if we want to. The vertical shift is 50. So there's the beginnings. And then phase shift is going to go with whether you're using sine or cosine, and you can use either. I would say, because I know exactly where some maximums and minimums are, cosine is going to be slightly easier. So I chose a cosine, but that doesn't mean you have to. What I was thinking, let me grab a different color, was this point right here is a maximum. That's 0.360. So a normal cosine wave hits its maximum right at x equals 0, which means if we just shift this to the right 0.3, we should be hitting our first maximum at 0.3 seconds. So I'm going to put a t minus 0.3, and that will line that up. So only one of the possibilities. There are infinitely many more, but I think that's a nice easy one to go for. Okay, the next question is really a technology question. What was the distance from the floor when you started the stopwatch? So you started the stopwatch at t equals 0. So you can plug that into a calculator, or I would say this is a great time to go to Desmos, check and make sure our function matches what we're expecting, and then also check what that y-intercept is to answer the second question. Okay, so I typed this in for you so you don't have to sit and watch me do it, but I have not adjusted my window yet, and I'm not seeing much. But remember, we did graph this thing. We do know about what we expect it to look like. So in particular, we need to see the y values between 40 and 60, and I went up to 3.3 seconds to get a full period, so I think I want to see at least that much. Let's see if I can get switched over. So I'm going to hit the graph settings, and I'm going to set my x-axis from 0. Let's even go to 5. We'll go a little more. And then my y-axis, let's go like -5 to, what was the top, 60? So let's do 70. And the only reason I do the -5 is to make it so that my x-axis isn't sitting exactly on the bottom of the window. And then actually I'm going to zoom out a little more because I'm realizing that the way I have my recorder set, you weren't seeing the very bottom anyway. So that's what my graph is looking like. We were supposed to, let's check it out, hit the maximum of 60 centimeters from the floor at 0.3 seconds and the minimum of 40 centimeters from the floor at 1.8 seconds. This is looking really good. And then the part B question was, what happens at t equals 0? And the answer is the height of the spring is 58.09 centimeters. So this last question, you do have to show your work algebraically, but then we can absolutely go back into Desmos to check our answers and make sure it looks reasonable. Part C is wondering when will be exactly 48 centimeters above the floor. So we've got our formula up at the top and we need to set it equal to 48. My first step will be subtracting 50 from both sides. We're trying to isolate the cosine. And then I'll divide everything by 10, giving me negative 1/5. And now I'm ready to think about the unit circle. So as soon as you've isolated your trig function, we're going to say, okay, that's when I get to say that the negative 1/5 is an x value on the unit circle. So I'm looking for a point in quadrant 2 and a point in quadrant 3. And to get me one of those, I'll take an inverse cosine of negative 1/5. So that becomes a technology question since it's not a special value. I'm getting roughly 1.77. So that, unsurprisingly, is going to be this top. And then for the bottom one, you could use a negative 1.77, you could use a 2 pi minus 1.77, whatever you'd like there is fine, anything coterminal. So back to my equation, what this means is that my angle, which is actually 2 pi over 3 times t minus 0.3, is approximately equal to plus or minus 1.77 plus 2 pi k. And to solve, I'll need to multiply both sides by 3 over 2 pi, which will just cancel out on the left-hand side and give me new numbers to work with on the right-hand side. So now I have plus or minus about 0.85, and I am saving my previous answer in my calculator and using it, so I'm not actually getting a bunch of rounding error on every step. If you're not able to do that, you might want to give yourself more like 4 decimal places to work with so that you don't get quite a bit of rounding error built up. And then when I do the 2 pi k times 3 over 2 pi, I just get 3k, which should be what we're expecting. We said our period should be 3, but I find that if I don't let the algebra do the work for me to get back to that period of 3, I will forget and I'll just tack a 2 pi k on at the end quite frequently. So my advice, if you're at all like me, is to just let the algebra fix that for you so you don't forget. The last step here is going to be adding the 0.3 to both sides, and then I'll have to work those two, the plus and minus, separately. So when I do the plus, I get 1.15 plus 3k, and when I do the minus, I get negative 0.55 plus 3k. I don't love the negative answer in terms of making sense in this context, although I guess we just started the stopwatch somewhere along the way, so saying it happened before the stopwatch started is fine. But note that you can just add 3 to get your first positive answer. And we're specifically looking for the one first positive value that we hit, 48. So we could check that. It's looking to me like the 1.15 is actually going to be it. I will get a 2.45 if I add 3, which is bigger than my 1.15. So this 1.15 seconds will be my answer. And we can switch back over, like I said, now that we've done this algebraically, and double check on the graph and make sure that that looks right. So to do that, you're going to plug into your y equals. We want y equals 48. And then we can just check it out here. We're looking for the first time, and I'm getting 1.146, about 1.15, which is exactly what we found. So absolutely use that. That's a powerful check. And then our last question is, at this time, is the spring rising toward the ceiling or falling toward this floor? And what I see is that from here, the height is decreasing, and that's distance from the floor. The distance from the floor is decreasing, so it's getting closer to the floor, so it's falling at that point in time. And that is the spring problem. Let me know if you have any other questions.